Okay, start. Even though not many students have joined yet, let me start. They will join and I will soon start. So last class I have discussed about T-beam. I have given a brief introduction about T-beam. We have discussed about the various features and what are the nomenclature that used for the components of T-beam, and we have discussed about the overall depth, how it has to be maintained, and what are the benefits of T-beam. That's all. Today I will discuss about the analysis of T-beam, where how how it acts and how to find out the various moment of resistance and the calculation for mu limit and xu limit. We will discuss about the moment of resistance, how to calculate for different cases, for different conditions of with respect to position under reinforced section or for over reinforced section. Okay, so as discussed in previous class, we have seen the various components of T-beam. Basically, we have two portions. The slab portion is called the flange, and the beam portion, the vertical member, the beam portion is called web. So we have flange width and flange depth, and we have also web width and web depth. So here we are dealing with this, and as you can see in the figure, the section of a T beam is shown with having width of flange as denoted as fix f, and depth of flange is, overall depth of flange is denoted as capital D suffix f. The width of web is denoted by B suffix W. The area of steel, the tensile steel, is denoted as AST, and the effective depth is denoted by small d. And the for the section, we have the strain diagram and corresponding stress diagram for the beam section. That is quite similar to your rectangular section. So the depth of neutral axis from the topmost compression fiber is at a distance xu. Okay, similar nomenclature is considered. The maximum strain is considered at the compression as 0.0035, similar to your rectangular section, and also for tension 0.87 Fy by Es plus 0.002 is considered for strain diagram. The level of for the strain and our diagram, it is similar to your rectangular section. That is the above the neutral axis, the compression part is partially rectangular and partially parabolic. So two sections are there, and the maximum stress at the compression is 0.446 FCK, and the compression is acting at a position of 0.002 strain level. So and that is at the depth of 0.42 XU. That is 3 by 7th of XU. And from there, the position where compression is acting, from there the distance of neutral axis is 4 by 7 XU. Okay, and value of tension is 0.87 FY AST. Okay, so all these values are similar. So you quickly draw this in a piece of paper. So because this drawing we will be referring for our upcoming calculations for understanding. So you quickly draw this. You have already you know this you drawing. So you quickly draw this. So while drawing this, when in exam also you are drawing, many students make a mistake that while drawing they draw the stress or strain diagram. They bring the tension part near your total depth. So one thing is to be kept in mind: the distance from the neutral axis, the strain diagram when you are drawing the rectangle, the triangle, that the depth is up to your the centroid of steel AST. Okay, so better you draw a dashed line that is running from your AST horizontally, and up to that only you draw your strain diagram and stress diagram. Okay, so that is to be kept in mind. So as we can see that neutral axis is running, that is passing along with your within your flange portion. Okay, the depth of neutral axis is less than your depth of flange. Okay, so this is one condition that we will be doing our analysis, and another condition is when this neutral axis will be falling below the flange part, means the neutral axis will be they present in your web portion. Okay, for these two cases, we will see the variation in moment of resistance, the difference in calculation. We will discuss. So I hope all of you have drawn this picture. Okay, now since we have drawn the picture, so let us see. Let us first see the stress block. So as you can see, the stress block is divided above the neutral axis is divided in two portions. One is your rectangular portion, and another portion is BEDC. Okay, BEDC, and another portion is BAE. The parabolic portion is your BAE. This position of the BE, the distance is 0.42 XU or 3 by 7th of XU, you can say. And this is actually corresponding to the strain at 0.002. Okay, and we will be discussing the uh, two cases for calculation of this moment of resistance for the depth of neutral according to your depth of neutral axis. That is, first case we will consider when the neutral axis is falling along the flange section, means xu, the value of xu is less than df. Okay, and next case we will consider when this neutral axis falls below the flange, means it falls on the web section, that is the value of xu is more than df. So for these two conditions we will check, we will see how this moment of resistance changes, how we have to calculate. Okay, next we have to also see. So let us first consider the first case, that is when xu is less than df, that is the when the neutral axis is along the plane section. So for this case, one thing that is very important we have to consider, that the when for this condition, when the neutral axis is along your flange section, then the this section, this t section actually behaves as a rectangular section, behaving as a rectangular section, and the width of this rectangular section is equal to the width of the flange, that is bf. Okay, this is very important point. Okay, and this value of, if so happens, if so does the, if this t section behaves as a rectangular section with the same width as of the flange section, that is bf, so the calculation becomes very easier. So the depth of neutral axis is calculated as a rectangular section, that is xu is equal to 0.87 fy ast by 0.36 fck bf. Okay, and similarly, we have, as discussed in the previous class regarding your rectangular section, the calculation goes similarly, where we consider the width as bf, and since it is a rectangular section, so for the cases where the section is under enforced or over enforced, means with respect to the value of xu, with respect to xu max, we determine the condition, and accordingly we can calculate the moment of resistance. So when condition is so from table 4 of IS code, we can get the value of xu max by d from the table for different steel section, and from there we will see that what is the value of x respect to xu max. If x is less than xu max, first condition, then moment of resistance is calculated as 0.87 fy ast into d minus 0.42 xu, since it is a under enforced section. And for balanced section, when the value of x is equal to xu max, then either this equation or the mu limit value, that is 0.36 fck into bf into xu max into d minus 0.42 xu max, this equation could also be considered. And if it is over enforced, then we know certainly it is not acceptable and we have to redesign the section. Okay, I hope this is clear to everyone. Now next, moving to next case, case 2, when the value of XU is more than DF. Okay, so for this we have to idealize this T beam. We have to idealize this T beam into fragments of the section. Okay, one fragment we will consider as you can see in the figure 5. We have in the T section is divided into two fragments. One is segment 1, another is segment 2. Okay, and accordingly we will do the analysis. So here the for singly reinforced section, the width of this section 1 is considered as BW, that is the width of web. Okay, and depth is considered as the effective depth of the beam, that is small d, and area of steel is kept similar, that is AST. And on the next case, for the next section, section 2, as you can see, two fragments of flange have been separated from the web portion. So that flange section, two flange sections are considered, and their depth is considered as the depth of flange itself, that is DF. Okay, and the width is considered as overall width of the flange BF minus the width of the web, that is BF minus BW, right? So if possible, you can draw this picture for better understanding. And if you have any problem, you can ask me. If you are having facing any problem to understand this figure 5. So this is the case where the neutral axis is falling at the web part, flange portion XU is more than DF. So for doing, we are actually taking two segments of this T beam. We are taking a vertical portion, the overall small effective depth we are considering for this section, and and we are considering another fragment we are considering of flange portion only, that is segment 2 as shown in figure. And the width of this vertical web portion, the overall segment 1 is width of the web, that is BW, and depth is small, effective depth is small d, whereas the segment 2, the flange portion is just subtracted, the overall length, overall width of the flange is subtracted with the width of web, that is BF minus BW. So we get two section two the second section is only the flange portion minus the web, and total depth of flange portion for segment 2. And the stress diagram, as you can see, is similar. Okay, the factors is same, that of this compression in the stress diagram, as you can see, is similar, that is 3 by 7 XU. It will be acting at that portion only, and um, the that force is CK. Now again here for this second case, we are actually the code has further classified this into two different cases. For this XU more than DF, when for we are calculating case for balanced section, second case when we are under enforced section. For balanced section, this XU max is equal to XU. Okay, for XU is equal to more than DF, and for under enforced section, the value of XU is less than XU max. Okay, sir, the 5.
Now moving to next portion, that is, let us consider case one, when the section is balanced, means the XU max value of XU max is equal to XU. For that condition, let us see what we actually dealing for this according to para G 2.2 in IS 456. Again we will have another two case, the two sub case of this case one, that is when the value of df, the value of uh, flange, the value of depth of flange is less than the value of the portion, the where the compression is acting, the value of c, when where it is acting, means the c is acting at a depth of 3 by 7th of xu. So we have to check that this value, whether this value of df, if it is less than 3/7 xu, okay, means the depth de, the portion de of the rectangular portion of the stress block, if uh, it is greater than the depth of flange, then this compression zone will completely lie on the rectangular portion of the stress block. Okay, and on the other case, on the contrary, when this df, if the compression part lies within the depth of flange, lies within the flange portion, that is when depth df, value of df is more than 3 by 7th xu. Okay, in that case, the means the compression zone will be lying within the rectangular, will means that is the the distribution of this stress will not be in the rectangular portion. Okay, it will be outside the rectangular portion, means it will be some part on the parabolic zone, on the parabolic portion of the stress diagram. Fine. So accordingly, uh, so since this value of xu max, we know that it is dependent on the grade of steel, whether it is for the different grade of steel where we get the xu max by d ratio different. So from there we can see the IS code has concluded that it recommends a single value of df by b, df by d, that is 0.2. Okay, I hope I'm just again repeating it. So we have seen the case one. So we are actually discussing the case where the neutral axis is lying below the flange portion. So for that case, we have two cases available. One is when the means d xu max is equal to xu. So again for this sub case, for a balanced section where xu max is equal to xu, we have two cases. The whether the compression zone will be lying completely, the flange is actually lying completely within the rectangular portion of stress block, or it is lying partially with also the parabolic portion of the stress block. Okay, because it will be necessary for our calculation to check. So for these two cases again, where df is less than or equal to 3 by 7 xu, means it is the portion of flange is completely lying on the rectangular portion of stress block. Okay, and another case is when my flange is uh, lying on the rectangular portion and also partially lying with the, some part is lying with the parabolic portion of the stress block also. Okay, so Indian Standard Code has given a simplified approach where we can recommend this value of uh, df by d. Means instead of like for rectangular section x max by d, the code has given df by d. Value of df by d as to be considered as 0.2. Okay, so based on this value of df by d, there are again two subcases, subcase 1a and subcase 1b. So under this subcase 1a, where the xu max is equal to xu, is more than df, that is the previous condition. So for that condition, df by d, df by small d is less than equal to 0.2. And for case b, case 1b, where xu max is equal to xu, but the value of df by d is more than 0.2. Okay, so actually this because of the 3 by 7 xu max, the value for rectangular section, if you consider for Fe415 steel, the 3 by 7 of xu max, that is 3 by 7 of 0.48 d, the value of I hope all of you are getting this. So that's why I asked everyone to draw the diagram so that things will be clear. Now let us discuss the case 1, where the subcase 1a, that is when xu max is equal to xu, but for the corresponding value of df by d less than equal to 0.2, or df is less than 3 by 7th of xu. Okay, this is subcase 1a. So so as per the given condition, uh, depth of flange, it is completely lying on the rectangular portion, means the rectangular portion is much greater depth than the depth of flange. So for this case, the total compression will be actually the compression of the rectangular section. Okay, BW D, compression of the rectangular section for first segment, and also the compression of rectangular section of segment 2, that is BF minus BW into DF. So as we have divided our rectangular section into two portions, two segments, segment 1 and segment 2. So for both the segments has to be considered for calculation of compression. So that is why total compression comes as BW into DF plus BF minus BW into DF. Okay, I hope everyone is getting this. If possible, you can draw this figure, figure 6.
Okay, and the total dimension is 7FY is that is for the rectangular section, that is segment 1 plus 0.46 FCK into BF minus BW into DF. That is for the segment 2, and that is comprising of your uh, rectangular stress block.
Okay, I hope everyone is getting this. Next, move to. So if you do the moment of resistance calculation uh, for the previous case, case 1, you will find that how will you get that? That is just a minute. So how will you get that? The moment of resistance will be, you have to just multiply with d minus 0.42 xu max for the rectangular section, and for uh, segment 2, that is for compression in the rectangular section of for segment 2 bf minus bw, you have to multiply with d minus df by 2. So instead of xu max by 2, you have to just substitute the xu value of xu max. Instead of that, you have to take df. So moment of resistance for case 1a will be 0.36 fck bw into xu max whole multiplied by d minus 0.42 xu max plus 0.446 FCK into BF minus BW multiplied by DF whole multiplied by D minus DF by 2. Okay. So this you can find in the IS code IS para G 2.2, the value of this MU. And let us see the second case 1B, second sub case where the value of df by d is more than 0.2, means the value of df is more than 3 by 7th xu, means
So for that, IS code recommends the value of mu that is given in para G 2.2.1 in the IS code. So here a factor YF is introduced. Okay, so the equation, as you can see in the slide, it is 0.36 xu max by d whole multiplied by 1 minus 0.42 xu max by d into FCK BW D square. Okay. So for this portion, for the web portion, it is clear. It is only the substitute is value is BWD. But for the portion where it is falling below the rectangular portion for the segment 1 part is clear, I hope. And the addition segment 2 part, there is a additional YF factor. The equation is 0.4. Finally, it stands as 0.45 FCK into BF minus BW into YF whole multiplied by D minus YF by 2. So instead of taking DF, here YF is considered, where the value of YF is 0.15 XU plus 0.65 DF. Okay, and this value should not be greater than DF. So IS code actually recommends a simplified approach. So instead of going for any complicacy for introduction of this parabolic section, a simple equation is provided by just replacing this df with yf with the value of yf, and the here instead of taking 0.446 fck, the value 0.45 fck is considered for the segment 2, for the calculation of segment 2 of flange part. Okay, so I hope all this is clear. Up to here, it is clear to everyone. If you want to repeat any portion, if you want me to repeat any portion, I can repeat. I hope it is clear to everyone. If you have understood the drawing, if you have understood the figure, you will be able to understand the equation why it is coming. Okay. Simplified equation is considered no complicacy, not much complicacy is there. Only cases you have to remember. I'm just recapitulating what we have discussed. So first case, what we have discussed, we have actually two major cases. One is when the neutral axis is lying along the flange portion. So if that, so that is well and good, and that is much simplifier because our whole section, the T section, turns as rectangular section. Okay, and the calculation goes similar to that of a rectangular section, considering only considering the width of the beam as bf, means the width of flange. Width of beam turns as the width of flange, that is bf, and using there instead of only the value of b, we replace it with bf for rectangular section, and the equation is similar to that of a rectangular section. But for second case there is some complicacy, and that is when the neutral axis is lying below the flange portion, that is xu is more than df. So for this xu is more than df, we have actually two sub cases. So one first sub cases is one sub case, okay, and another sub case we have discussed, that is for under input section. So we are till now we have discussed the balanced section for the second case. So the balanced section now again has two sub case. This balanced section again has two sub case. That is when this we have considered the value of we have this subcase again has two cases. That is when we are actually doing what we are we have for the case 2, when the neutral axis is lying below the flange portion, we have divided our segment into two portions, segment 1 and segment 2. The segment 1 is comprising of the whole web portion plus the portion of web, plus the portion of flange also. For segment 1, a full rectangular section is considered, and segment 2 is comprising only the flange portion minus the web portion. Okay, so considering these two sections, we are going to calculate all our compression and tension, and finally the moment of resistance. So for sub case 1, where again we have two sub cases. One sub cases, that is when we are actually considering df by d, the value of df by d is width of uh, flame divided by effective depth as recommended by IS code is to be considered 0.2. So when it is less than 0.2, less than equal to 0.2, then we have to do one type of calculation, and if it is more than the value of df by d is more than 0.2, then we have to take it again, take a different value of consideration. Means what? If since we know that the flange the since we know that uh, the stress diagram of the this rectangular section, as we have seen, it is comprising of a rectangular section as well as parabolic section. The rectangular section is BEDC, and the parabolic section, as you can see in the figure, is BEA or a BAE, whatever you say. So mm, this parabolic, so when again we have two cases, when this stress diagram, when the flange is within falling your rectangular portion, that is BCDE, if within this range, within the depths of DE, that is 3 by 7th XU,
it is falling, then our calculation is to be considered segment 1, taking considering the segment 1 and segment 2, that is for the compression to be calculated for rectangular section BW into D, and the compression for the rectangular section BF minus BW into DF. Okay, but when this depth of flange falls below the rectangular portion, falls below the rectangular portion BCDE, means it will also having partial portion of para, parabolic portion of the stress block, that is BAE. So for that condition, means for DF more than 3 by 7th XU, we the code actually recommends uh, DF with YF. So this YF is actually 0.15 XU plus 0.65 DF. So if we replace it, we can simply get no much. The code recommends a simple value. The code recommends simple values, and not much complexity is there. Okay, now moving to the next case, that is case 2 for under enforced section. This is the sub case. Sub case of the case 2. Okay, so sub case 1b, when for under enforced section, okay, one means XU max is more than XU. For this case, again, two sub cases are considered. Okay, sub case 2a and sub case 2b means when the value of df will actually, df by xu will actually be lying within 0.43, and another sub case is when df by xu will be more than 0.43. Okay, so let us see the first sub case. Uh, See, I was talking about sub case 2a. Okay, so sub case 2a, where our where our moment of resistance of this section depends on the value df by xu. Okay, so this condition is also again divided into two portions, where df by xu is less than 0.43 and df by xu is more than 0.43. So for this less than 0.43, that is sub case 2a, let us see how the calculation is done. For this, we have to consider the value of df. We have to consider the, for the entire flange portion, it will be lying within the stress block. Okay, if you have drawn the figure 6, if you have drawn the figure 6, then you will see that if the case when the complete depth of flange lies within the rectangular stress block, BCDE, then the total compression is calculated as given is 0.36 FCK BW into XU plus 0.446 FCK into BF minus BW into DF. Okay, and the tension will be similar, that is 0.87 FYAST. Fine, no problem with here, I hope. Now of resistance, we have to just multiply it with the value of d minus 0.42 XU and d minus 0. D minus df by 2. So, and to get the value of neutral axis, we have to just equate the total compression with total tension to get the value of neutral axis. So from equating both the equations, we'll get the value of xu and the value of mu. Moment of resistance can be obtained by just multiplying with the factor d minus 0.42 xu. Okay. For the first segment, it will be d minus 0.42 xu, and for segment 2, it will be d minus df. Sorry, df into small d minus df by 2. Okay, because the depth of segment 2 is df, and the depth of first segment 1 is the rectangular block itself. So that is why it is 0.42 xu. Okay, I hope this is clear to everyone. Now next, let us see case 2, where the value of this df by xu is more than 0.43. So for this case, where the value of df is more than 0.43, we have actually we have to consider the depth of this rectangular portion that is lying within the stress block and is less than the depth of the flange. Okay, so for this, we are again considering the factor yf. Okay, and the depth, and to calculate this depth of neutral axis, we have to equate the total compression with the total tension. Total tension remains the same, 0.87 FIST, and total compression will be in terms of yf. Okay, because we have to consider the portion below the rectangular portion. So actually, what IS code has done, for the ease of calculation, means for the parabolic portion, it has, whenever the any parabolic portion of the stress block is coming, it has considered the factor yf. Okay, and the condition is it should not be greater than the value of df. So whenever the depth of flange is reaching below the rectangular portion, just remember you have to consider the term yf in your equation. That is zero. The equation turns as 0.36 FCK into BW into XU. Okay, that is the segment one, and for segment two, it turns as, so remember, for segment okay, on because that will be for a rectangular section, that will be considered for only a simple BW into XU value, but for flange portion, we are considering this parabolic section. So that is why F is included. That is 0.45. So don't consider 0.446. Consider 0.45 FCK into YF into BF minus BW. That is equal to 0.87 FI AST. So with this equation, you can find the value of XU. And finally, the moment of resistance mu can be find out by just multiplying the lever arm. So for rectangular portion, we have to multiply d minus 0.42 xu max. Sorry, d minus 0.42 xu. So since it is a segment one is your rectangular portion, and for segment two, you have to only consider multiply the lever arm as d minus yf by 2. Okay, so this parabolic portion yf is considered. So simply multiply with d minus yf by 2 in your equation. to get the final moment of resistance. So you can find all this equation in para G 2.3 of IS code. So the last portion is the over-enforced section. So as we have discussed, the over-enforced section is not recommended. We as we have previously discussed, because we know for a over-enforced section, the failure will be sudden. The failure of the structure will be sudden and without any warning. So that is why over-enforced sections are avoided, and we recommend the IS code recommends redesign. Limit is to be taken considering extreme circumstances. Okay. I hope today's class is understood by everyone.
Yes, sir.
Okay, all of you write your name and roll number in the chat box for today's attendance. If you have any problem, you ask.